So, I think what Chandan talked about in Landau diamagnetism, he talked about the expression that you get when you have magnetic field in the presence of free electrons. And what Shivang is going to show you is that energy expression remains the same irrespective of what gauge you use to solve the problem, which it should be, because gauge is a trick to solve certain problem. It should not have an impact on the physical result, right. So, we will solve the same problem in two different gauges to show that the energy expression remains invariant to the gauge you choose. Okay. So, I will talk about time reversal symmetry today. We start with the time dependent Schrodinger equation. Okay. So, now let me ask you one question. So this psi is psi of x and t, right. So, it is a function of x, function of t. So, if I replace x with minus t with minus t, is that a solution to the Schrodinger equation? Yes or no? Yeah, why? Right, that would be minus, right. So, if you just replace this here, replace t with minus t, this would be minus. So, there will be a minus sign in front, right. So, it is not the same Schrodinger equation that we will get. But let me do one thing, let us take the complex conjugate of the whole equation. Okay. So, I get minus I h bar del t psi star, minus h bar square 2m del square, and assuming that v is real and everything, I have this equation, right. If I take the complex conjugate of this. Now, if I replace here t to minus t, then I get back the Schrodinger equation. Right. You see that if you remove that psi square, everything is the same as above. So, all we did is to take a complex conjugate, replace t with minus t. So, psi star x of minus t is the solution of the Schrodinger equation. So, it seems that if we have to change t to minus t, somehow we need an operation that will also do complex conjugation, then everything is consistent, right. Okay. So, this is the general principle in time reversal symmetry. In time reversal symmetry, we talk about switching the motion of the particle. So, it is going in some direction, then we switch the motion after some time, right. And in that case, it seems in quantum mechanics at least, you need operators that not only does that switching, but also does some kind of complex conjugation. Okay. So, we will define the time reversal operator in a certain way, and we come back to that, what would be the form of the time reversal operator and so on and so forth in the subsequent lectures. So, we will have two properties. One is that, let us say this we start with some state alpha, okay, and then we operate this with some operator which we will call as the time reversal operator, and we get a transformed state alpha tilde. Similarly, we do for beta. Now, what we are saying that instead of, in general, what happens if you have a transformation, for example, rotation, right. You have two states that are rotated in the same fashion with the same evolution operator. Then, if you take the dot product of them or the inner product, that the inner product is invariant to that, right. Because what happens in general is that if you have some transformed prime with some operator u alpha, and if you operate the same operator on another ket beta u beta, you take the inner product, right, inner product of let us say beta prime alpha prime, then you take the dagger of this thing. So, beta u dagger u, right, and u dagger u is an identity, right. So, you transformed in certain direction and then you take the dagger, it is transforming in the other direction. So, as if you are doing nothing if you are combining them together. So, this is an identity which means that your inner product did not change if you had a general transformation, unitary transformation. Okay? But that is not going to be true in time reversal symmetry or time reversal operator. So, what we will instead say that this thing, the fact that the inner product has to be the same will not obey that, but what we will say is that the mod of the inner product has to be the same, right, which gives us some flexibility, because now then we can say that your if you do time reversal, then it can be a complex conjugate. If this is true, then this mod is also the same, right. Of course, if the transformed is the same as the initial one, then the mod would be the same, but this gives a little flexibility that the mod remains the same, because mod in many cases is a measure of the norm, right. So, the mod remains the same, but it can be its complex conjugate. Okay. That is one property we will impose on the on this operator, and we will come back why that is so. The second property is what is known as the antilinear property, which means that let us say you have an operator like this and you have some combination of the kets. Okay. So, in general what happens that since most of the operators in quantum mechanics are linear, that will go through it and you will get something like C1 alpha plus C2 beta, right. In general that is true. For linear operators that is true, but for antilinear operators the way it is defined is that if you want it to go through, these coefficients would become complex conjugates. That is known as the antilinear property. Okay. And if some operator obeys both of these, that operator is known as anti-unitary. Okay. That is as a definition we are starting with, and we will show that to maintain or to obey time reversal, meaning that if you define a operator that would commute with the Hamiltonian, so that Hamiltonian will have time reversal symmetry, then these properties would be very, very essential. We will come back to that. Yeah. So, let us say I take an operator, right, operate on some ket alpha, and I get the transformed ket alpha tilde. Similarly, I do for the beta, then I take the inner product of the transformed kets, right. If that turns out to be the complex conjugate of the original inner product, right, that is one property. The another property is that if you use a linear combination of kets and use the operator, then the coefficients become complex conjugates, right. Usually it won't, right. If you have a unitary, the coefficients would remain the same and the operator will operate just on the ket. This is known as antilinear property, and both together if some operator obeys, then it would be an anti-unitary operator. Okay. then here is the claim we are going to make. That we will define our operator, some operator theta, as a product of the unitary operator, any unitary operation, and a complex conjugation u times k. Okay? So, this is a operator which is an unitary operator, and this is a complex conjugation. So, all it does, if it hits a some scalar, it will give you the complex conjugate of that. Together, if I take the product of these two, we will show that that follows an anti-unitary. I have phone. Oh, I see. Ring. Sorry. Yeah. But it didn't ring. I don't know. So, our claim is that, so if I take a product of a unitary operator and a complex conjugation operator, then that product will be an anti-unitary operator, and we will show that that is true. Okay. So, the way we will proceed, let us say I start with some transform kate, which is defined as theta alpha, right, and we will expand that in some basis, because what we know that complex conjugation actually works on scalars, right. How do you get scalars? You get scalars by expanding in some basis. So, the coefficients would be scalars. Okay. So, our let us say our basis is A prime. You know, when I take usually quantum 1 class, I tell that okay, you can forget everything about quantum mechanics, but if you have to take home one message from this class or one formulation, that would be resolution of identity. If you know resolution of identity, you can do a whole lot of things, right. What is resolution of identity? Is putting 1. You have to understand where to put 1 and what is that 1 composed of, right. If you know that, you can do lots of applications that are out there in papers, books, and so on and so forth. For example, when we want to insert a basis, we want to insert an identity operator here, right. So, identity operator is sum of A prime, A prime, A prime, right. So, that is an operator. This is a kate, right. If you have, I think all of you possibly know this, but if you have a bracket combination, that is a scalar, right. If you have out product, that is a product. This is known as a dyadic product, that increases the rank of whatever thing you are talking about. So, here we are talking about vectors, right. These kates are vectors. You take an inner product, that is a reduction in rank. So, from vectors you go to scalars. You take an outer product, that is an increase in rank. So, you make a matrix out of it, and matrix is a representation of an operator. Okay. So, identity operator is defined like this basis. So, we assume that the basis we are working on is a complete basis. I insert an identity there, I will have sum over A prime, A prime, A prime alpha. Okay. So, this is equal to u of k sum over A prime alpha, A prime. This k operates on the scalar, right. It does the complex conjugation of that. So, this is equal to u of sum over A prime alpha star, and then the u of course is a unitary operator that operates on your kate. Okay. Similarly, let us do beta sum over A double prime beta star u over A double prime. Okay. Now, here is a subtlety that you should remember, that when we are trying to get the inner product, we have to generate the bra out of it, right. Inner product is a product of the bra and the ket. Okay. So, the bra space is slightly more complicated. So, always work with what is known as a dual correspondence. Start with a ket, right, and take the dual correspondence of this. When you take the dual correspondence of this, so let me write it here, beta sum over A double prime beta star u A double prime. You take a dual correspondence, meaning that if you have unitary operators, that will become a dagger and the kets will become bra and the coefficients will become, will just flip. So, you have A beta and the order will switch. So, you have bra of A and u dagger. That is the dual correspondence. So, the dual correspondence will change the ket to bra and the operators to its dagger and the coefficients to its complex conjugate. That is what the dual correspondence does. Okay. Now, take this inner product. So, you have sum over A double prime, sum over A prime, A double prime beta, and we have A prime alpha star and A double prime u dagger u A prime, right. Are you clear on this expression? You have, so this is the expression we are using. This is one expression and this is the other expression. Okay, and we are taking the product, this and this, sum over A double prime A prime, and we have A double prime beta, sorry, A double prime beta, A prime alpha star, A prime alpha star, and you have A double prime u dagger, which is this, and u A prime, right, which is this. Now, u dagger u is identity, right, and we have taken a complete orthonormal set, which means that A double dagger has to be equal to A prime, sorry, A double prime has to be equal to A prime. So, this is equal to A prime, and let me write it in slightly different way. I can write it as beta A double prime star, or let us do the other way around. We call this alpha A prime. So, star of this would be switching the order, right. A prime alpha star is equal to alpha A prime, yeah, and these are numbers. So, the order does not matter. I take it in front, alpha A prime and A prime beta, because of this overlap between A double prime and A prime, we know this is the orthonormal set. So, it will be 1 only when A double prime hits A prime. All other cases it will be 0. Another way of writing it is this is a delta A double prime A prime, right. Okay. So, get speed of A double prime, sum over A double prime, and you have this. this is equal to, now again what is sum over a prime, a prime, a prime, that is an identity operator. So, this is equal to alpha beta, which is equal to beta alpha star. Okay. So, here since sum over a prime, a prime, a prime, okay. So, see all this derivation relies on one thing, how well you know how to write 1, right, and where to insert 1, where to take 1 from, that is it. We started with, so let me, this is a very important, this kind of derivation will come again and again and again in quantum mechanics. Yeah. So, you start with some transformed Kate, and we define the Kate as
Sir.
something. Yeah.
The operator K, it
Yeah.
acts on scalar, no sir? So
the operator K only operates on this.
But why don't the get vector?
Get vector.
If it is a complex.
Yes, but you see that this is a basis vector. What are basis vectors? Basis vectors zeros and 1. What is there to complex conjugate?
Okay.
Nothing, right? So, the complex conjugation will work only on the coefficients, not on the basis vectors. Basis vectors would be unchanged with the complex conjugation. That is a very good question. Okay. So, carefully look at the derivation, right. There are 2 points here that you should keep in mind when doing this kind of derivations. One is that when you are expanding any Kate in the basis vectors, you see that I have deliberately taken different notations, right. I have taken a prime here, a double prime here, but these are dummy indices, right. I could have taken a prime here, does not matter. Where it matters is here. Here you cannot take a prime, that would give you a wrong elements. So, that is one important component of these derivations that you should keep in mind. And the second is the order of these scalars, they do not matter because they are scalars. So, you remove, rearrange them in certain way so that you can take out 1. Okay. So, that is very important, please go through it once you go home or something. So, that gives us confidence that we can use this kind of an operator as an anti-unitary operator. Okay. This was the whole point of doing it. And of course, the other property, antilinear property, is very straightforward. You have a product of 2 operators, and if you use a linear combination of vectors, then K will operate on the coefficient, will conjugate that, and then unitary operator will operate on the other case. Okay. So, that is not difficult. So, this was slightly more involved, but if you have done this kind of derivation, it should not bother you too much. Okay. Now, let us come to time reversal. Let us say I have an operator, I have a Kate alpha at initial time t0 equal to 0. Now, I evolve it in time. Okay. So, this is my state alpha that has started at t0 equal to 0 and evolved to time t equal to t. Okay. So, at this point in timeline is t equal to delta t. Now, I am going to do 2 different operations with this. Right. So, let me make sure that, let me write it this one above. Okay. So, I am going to do 2 operations. One is that I am going to say I will apply the time reversal operator on this. So, let me represent it that in the time reversal operator it is facing on the other side, just for schematics. Okay. Do you want water? Okay. And then I let it evolve for delta t time. So, this kate at this point is the time reversed kate. Okay. The other operation is that let me look at the history of this kate and say what is the state of the system that has evolved from t equal to minus delta t and evolved up to this time, right. So, let us say this is up to this point that has evolved up to this point, this is t equal to minus delta t. Okay. So, at this point the state of the system was t0 has to be 0, but t equal to minus delta t, and then I apply a time reversal operator on that. Okay. So, if the Hamiltonian is symmetric with respect to time reversal operator, then these two states should be exactly same. So, what are these two states? Either I start with this. So, my evolution is 1 minus I h by h bar delta t theta alpha, that is the state. That should be exactly equal to, if I had evolved the state first with minus delta t, okay, or in other words minus I h, and the delta t is a constant. So, that cancels out, theta some kate, right. So, this property should be independent of the kate. The formulation we are doing is equal to, so this minus minus plus, and then of course, the first term is the same, right, which is theta alpha. So, theta I h some kate, it is I h. Okay. Now, see, if I take this I out, cancel with the I, then we will have all sorts of problems, because we will end up with some formulation like this, minus h of theta would be theta of h, and you can show that if this is what happens, then all the physical quantities becomes really unacceptable, right. But we have something to save us here. We have said that we define the time reversal operator with something called conjugation, right. So, if I have to take this out, that will be minus I. So, this is equal to minus I theta h. Now, we are good, cancels out, h theta equal to theta h, which implies that theta and h to each other. That is what it should be if the Hamiltonian is invariant under time reversal operator. Right? Yeah. So, any invariance means that the Hamiltonian will commute with that operator, right. And here, since we are saying that our Hamiltonian is invariant under time reversal, that means it should commute with the time reversal operator. And the condition for it to commute is that it has to have some kind of complex conjugation. That is where it comes in handy. Otherwise, this relation will not hold. Okay? Okay. Any questions so far? You should carefully go through the steps, because there are some subtle concepts that are added here, right. and let me know if you have questions later on. Okay, what else do we expect? So let me erase this part. The other property that we would expect is that, let us say this is a momentum operator, and as I said, time reversal is basically meaning you are reversing the motion of that particle, right, and momentum is what causes translational motion. So, you would expect that under this transformed Kates, the expectation value of the momentum would have reversed. So, this is should be equal to alpha p alpha, that is our expectation. Our operator, whatever we generate, should obey this. But what about position? Can you tell me what about position? Should it be transformed? No, right? Because it does not matter whether I am going in this direction or this direction, the position eigencase remain the same. So, this should be equal to alpha x alpha. Now, of course, in this case you can put the theta and theta inverse, and you can show that this statement is same as saying that if you do a similarity transformation of p with respect to theta, that gives you minus p, and if you do the same thing with x, that gives you x. Okay. So, if that is the case, let me ask you to derive something. Okay. Given these informations, can you derive what happens to the commutation relations of x and p? That used to be I h bar. Forget about the delta for Dirac delta notation or Kronecker delta for a moment. Just assume we are dealing with x and px, and tell me what happens if you introduce the time reversal operator here. What would happen to this commutation relation? That is very important, right? We have built a lot of physical phenomena based on this commutation relation, right? So, under time reversal, if the commutation relation changes, we will have different physics. So, can you figure out what happens to these commutation relations if I use time reversal? So, the way you are going to do it is approach the problem is using this. So, you start with this x px sum ket alpha equal to I h bar alpha, right, and use an identity here. So, identity would be theta inverse theta, and then on the left you operate theta, right. So, that you get term like x px theta inverse, okay. That is what you want. That is the similarity transformation of the commutation relation. So, please try to derive, given this constraint that the similarity transformation of your momentum will give you negative, and the position is invariant under similarity transformation with your time reversal operator. Okay. Try to derive this. So, for first step we should expand this commutator, right. And whenever you have a product like you will have x p x kind of products, right. When you have a product, insert an identity in between, and then you know the transform properties. So, for example, if you have a quantity like this, you do not know what that is. So, insert an identity here I equal to theta inverse theta. So, you will get theta x theta inverse times theta p x theta inverse, that you know how to do, and so on and so forth. So, what do you get for the left hand side? What is the, so if you operate this, what is the left hand side? Loud, whoever is saying loud. See, the same thing can come from two different sources. One that you already know the same thing will happen, the other you derive the same thing happens. So, I have to check which one this is. Yeah, of course, they might converge, they should converge, but it is the job in this class that they would to see how it converges, right. So, what is the left hand side? What is the product of this? What this one you will get x, right. This will be minus px, right. So, if I do this part, then I should get x minus px theta alpha. Okay. Yes or no? And that is not the same as xpx, that is minus of xpx. Okay. So, that changes sign. What am I doing wrong? Am I doing anything wrong? Okay. What about the right hand side? Minus I h bar, exactly, minus I h bar theta alpha, right? Because you have a complex conjugation, you have to, if the I passes through theta, it gains a phase factor of -1. Okay, now we are fine. So, the minus minus cancels out and we get back to the same commutation relation. Okay. So, given the definition we had for time reversal operator, the commutation relations does not change, which is a good news, right. That means, all the physics that we have constructed over based on the commutation survives. Okay. Now, we are going to prove a theorem, very simple theorem, but a powerful one. That theorem tells us that if theta commutes with h, meaning that the Hamiltonian has time reversal symmetry, and if we are talking about a spinless particle, right. So, spinless system. Also, if the system is non-degenerate, meaning that it does not have any degeneracy. So, no degeneracy, then the wave functions are real. Okay. So, in in postulates of quantum mechanics, Hermitian operators, you talk about eigenvalues, right? Not eigenvectors. You did not have anything to talk about eigenvectors or the wave functions. Wave function could be anything, but this is an interesting theorem that comes from time reversal symmetry, that if the Hamiltonian is invariant under time reversal operation, and if it is spinless, and if there is no degeneracy, it turns out that the wave function has to be real. Why? Let us prove that. So, let us start with some ket n, right? That ket, so this is the proof. We start with some ket n, which is an eigen function or eigen ket of H, Hamiltonian, okay? And it has the energy E of n. So, if this is, if theta and H commutes, we can switch the order. So, this is theta H of n, which is theta E n n, which is E n theta n. Okay? Since we are assuming that our energies are real, which means that if they do not have any degeneracy, the n and theta n are the same state, right, because they have the same energy. The only way they can have the same energy are either they are degenerate or they are the same. Degeneracy is cancelled by your postulate, so they has to be the same. Now, if you project onto the x coordinate, that is our wave function. What happens to the left hand side would be the x n, but right hand side we know what this operator does. All you get is a complex conjugate of that. Now, if something is equal to its complex conjugate, that has to be real. Okay? So, that means the wave functions are real. Physically you can look at, of course, you can, in classical motion you can do it. In quantum mechanics, there is an inherent symmetry that might come out. That is why all these operations are going on, right. Of course, just having this property does not ensure there is a quantum number. For example, any for angular momentum we did, right. If angular momentum comes with the Hamiltonian, a square or a z might be a good quantum number, right. But that is not true here, because theta is not unitary. That is only true for unitary operators. But so there is no conservation law as such, but we can get some additional degeneracy that we will see if you have this kind of symmetry. So this symmetry comes from the property of the equation that is obeys. The way classical mechanics obeys, it is already time reversal symmetry is there inbuilt. But here, because of this I sign, there is some complications. That is why all these things comes about. Okay. So, we have now without proof I will make a statement, and that is a powerful statement, but the proof is little bit more involved. Maybe I will ask Shivang to do it. So, Shivang I think has not been able to come today, I do not know why. So, here is the property. So, theta square, right, theta is our time reversal operator. For half integer spins, it is actually -1 and is equal to 1 for integer spin. Okay. For half integer spin, you can work out that by using the general form of the spin eigenstates. Slightly more complicated. It requires you to solve the spin eigenstates and see what is the expression there. So, we will not go in details about that, but that is some result that is very, very important, right. Now, we will see what is the concept. So, we have already seen this part. This part is this, we have some spinless system. So, this part will give you this thing, that the eigenstates are real, but what about this part? Does it have any consequence? So, let us see. We will start with the same point, that if we have time reversal symmetry, meaning that if the theta commutes with h, right, then n and theta n will have the same energy, right. And here again, as I said, there are two options, either they are the same or they are degenerate, right. Now, let us assume they are the same for a spin particle, which means theta n equal to some phase factor times your original kth, right. Now, if I operate theta on that, theta square, then of course, you will get a complex conjugate of this, and product of that. So, you get minus I delta over I delta theta n, right. This 2 is 1 and this is n, because theta n is equal to n, which means that theta square equal to 1, which is not possible. So, for half integer spin, if we follow the same derivation, right, the only choice you have got are the fact that n and theta n are degenerate. Unlike the spinless, we said that they cannot be degenerate, and then we got the option that they have to be the same. They have to be the same result got us real eigenfunctions, and the fact that if they become same, then theta square is 1, which cannot happen for half integer spin. Half integer spin theta square is -1. So, what is true is n and theta n are degenerate. Okay. This degeneracy is known as Cramer's degeneracy. Yes. Yeah, +1 is easy to show here, but -1 is slightly more complicated. So, you have to start with the spin eigenfunctions and then work out what the theta would be. See, the principle is the same. You start with plus, operate on theta. What you get is some factor times minus, because it is an angular momentum, right? Plus. So, it will switch the thing -1, and then you start with minus. See how the minus looks like in that basis. Compare them to. Then you will get that theta square has to be -1. That is the principle. But since eigenfunctions of the in general, that is a problem by itself. We do the problem that what is the form, what are the eigenkets of this? This is a direction in space. So, norm is 1, okay, and this is this general S vector is Sxi plus Syj plus Szk. Then what are the eigen vectors of this? That you should try at home, but maybe in one of the tutorial you will do that homework. That is a very interesting problem. All you have to find is what is the matrix corresponding to that and diagonalize the matrix. You will get the generalized spin eigenkets. And then you can see that how you can write that spin eigenstates in terms of rotation operators. And then this derivation is pretty simple. Okay, so this Cramer's degeneracy is inbuilt in the Schrodinger equation, and it cannot be lifted if you have any electric field. But if you have something like a magnetic field that couples either the vector potential or the spin, right? Because if you have a spin operator, for example, you have been doing all the Mustansi thing, S dot L kind of thing, right? The spin orbit coupling, that will lift the degeneracy, but an electric field won't. On the other hand, something like crystal field, that's an electric field, that would lift some degeneracies, right? Doesn't matter what the spin is. Okay, so I think I am mostly done for today. So we'll have few minutes of question and answer, and you are more than welcome to email me if you have questions and doubts about this. And I have already talked with the tutor, so he will do one problem on how to do addition of angular momentum, and one problem on Landau levels, how to derive them with different gauges, Landau gauge and symmetry gauge, and maybe one of these problems where theta square equal to -1 he will derive and such.
Okay, wonderful. Thank you, Soumya. So, questions, comments, suggestions? Yeah. You have a question, tell me, because we want it recorded.
So generally, if operator commutes with the Hamiltonian, then it is a constant of motion. No?
Right. That
But
is only true. That conservation law is only true if you have an unitary operator. So this time reversal symmetry commuting with Hamiltonian in general doesn't give a constant of motion, but it has some consequences, as you have seen. Depending on the system, you can have real wave functions, or you can have some inherent degeneracy. So these conservation laws sometimes will lead to degeneracies, right? So this is one case where it might lead to degeneracy, but that depends on the system.
Good. Something else? As he said, of course, the tutor will be there, but nothing better to hear it from the lecturer. So, any doubt, even in the earlier, in fact, anything from the earlier teachers also, he can mention. Yes, no? Okay, if there are no other questions, we'll end here, and thank you. And there is another talk. Okay, there'll be a break. Tea break will come. It won't come now. And but after tea, Professor Shiv Prasad is here, and he will give the first of 2 lectures today. It's up there. Huh? Yeah. Anything you want to say, Professor? No. Okay, good. So we'll disperse now, but come back for the lecture after tea.